Hello, everyone, and welcome back to the EV Geek Studios. I'm your host, Joel. Today is Wednesday, June 17th, 2026. Had to check the date. We hope everyone's having a great week. A huge shout out to my co-host and buddy Sebastian for covering for me last week on short notice. We had some college visits we had to do with my oldest. It was great. Got to spend some family time together with him. And once again, thank you, Sebastian, for filling in for me last week. But enough about last week. Let's talk about this week because today we are talking about Tesla. For months, the Tesla Cybercab has been wrapped in a layer of classic Silicon Valley showmanship. We saw it roll onto movie sets. We watched the glossy presentations and we listened to vague promises about efficiency. But what we didn't have were the official, certified, government stamped specifications. That's until today. The official EPA certification documents for test group TTSLV00.0L1A, mouthful, have leaked, and the certificate summary information, or CSI, was officially finalized by the EPA. This is the blueprint. This is the raw data that Tesla legally must file to introduce a vehicle into U.S. commerce. And when you look at the raw metrics, they tell a radically different story than what the general public expects. We aren't talking about driving impressions today because, quite frankly, there isn't a steering wheel to wrap your hands around. Instead, we're doing a deep dive forensic analysis of the vehicle's powertrain architecture, battery weight distribution, and the highly unusual aerodynamic and electrical compromises Tesla engineered into this machine. If you think the Cybercab is just a stripped down Model 3 with 2 fewer seats, the data proves you are entirely wrong. This is a highly specialized, aggressively optimized piece of fleet machinery. But it also reveals a few engineering head scratchers that suggest Tesla is fighting a brutal war against physics. Let's break down the headline figures first, and we'll dive into the details later. Then we'll look at architectural choices under the skin. The EPA filing confirms 3 core pillars: a curb weight of 3,113 pounds, a peak output of 219 horsepower, and a usable battery capacity of roughly only 48 kilowatt hours. On paper, those numbers look modest, almost, you could say, boring. But when you map them against the vehicle's physical dimensions and its target use case, they reveal a masterclass in efficiency, mixed with a few stark compromises. Before we get started, as always, don't forget to like and subscribe so you know when new content is released. We love having y'all watch our videos. So now let's dive in and learn more about the Tesla Cybercab. All right, so let's start with the most shocking number in the entire document, at least for me, and that's the weight, 3,113 pounds. So when Tesla first introduced a dedicated 2-seat robotaxi built from the ground up, the immediate assumption across the automotive engineering space was that this vehicle would be an absolute featherweight. It has no steering wheel, it has no mechanical pedal assembly, it has no rear seats, no rear doors, no window switches for a second row, and no traditional dashboard architecture. Yet, at 3,113 pounds, the Cybercab is surprisingly heavy. To put that into context, a Mazda MX-5 Miata, which is also a dedicated 2-seater carrying a combustion engine, a transmission, and an exhaust system, weighs roughly 2,341 pounds. The Cybercab is nearly 800 pounds heavier than a Miata. Even more telling, a standard 4-door 5-seat Honda Civic gas car weighs around 2,877 pounds. Tesla's 2-seat minimalist future capsule is heavier than a standard compact family sedan. Now, to be fair, it is roughly 750 pounds lighter than a base Model 3 rear-wheel drive, which tips the scale at over 3,800 pounds. But remember, the Model 3 has a significantly larger footprint, 3 more seats, and a battery pack that is over 12 kilowatt hours larger. So where is the weight hiding? Part of it is obviously the battery. The EPA document lists the pack at 326 volts with a capacity of 146 amp hours. That calculates to roughly 47.6 kilowatt hours. According to the filing, the specific energy of the pack is 154 watt hours per kilogram. Do the math on that, and the battery cells and structural casing alone account for roughly 680 pounds of total mass. But that still leaves more than 2,400 pounds of vehicle. If you strip away the driver controls and structural bulk of a traditional five-seater, where did that mass go? Well, I think the answer comes down to two factors: structural crash safety for the steerless cabin and autonomous redundancy hardware. Because the Cybercab features an open, continuous cabin layout without a traditional dashboard or steering column to act as a structural load path during a front collision, Tesla had to over-engineer the lower floor plan, side seals, and front crumple zones to absorb a massive front crash force. Additionally, the redundant active safety systems, the dual compute enclosures, the independent routing for power delivery, the camera arrays, and localized cooling loops for the AI hardware add fixed weight overhead that a normal vehicle simply doesn't carry. Tesla didn't build an ultralight hypercar. They built an armored vault for 2 passengers, optimized to survive a high-duty psycho-urban environments. The gross vehicle weight rating, or GVWR, is listed at 3,700 pounds. Subtract the curb weight, and you get a total maximum payload of 617 pounds. That is tightly calculated. 2 standard adult passengers and 2 large suitcases will push this vehicle right up to its legal engineering limit. There is zero wasted headroom here. Now, let's get to the powertrain, because this is where Tesla made a complete U-turn from a traditional engineering philosophy. The EPA filing lists the motors as a 3-phase AC permanent magnet motor rated at 163 kilowatts, which translates to exactly 219 horsepower. But the real kicker, the drive configuration is explicitly listed as front-wheel drive. For anyone who has followed Tesla's engineering trajectory, this should make you pause. Outside of the dual motor all-wheel drive configurations, Tesla's single motor vehicles, the Model 3, the Model Y, and the historic Model S, rest in peace, have always been rear-wheel drive. Rear-wheel drive provides better performance dynamics, handles immediate electric torque transitions cleaner, and aligns with a more premium vehicle layout. So, why did Tesla swap to front-wheel drive for the Cybercab? Well, it's an aggressive play for packaging efficiency and cost reduction. In a traditional rear-wheel drive EV, the motor sits between the rear wheels, which requires a robust rear subframe, complex multi-link suspension geometries, and cuts significantly into rear cargo volume. So by shifting the entire drive unit, the motor, inverter, and single-speed gearbox to the front axle, Tesla completely frees up the rear of the vehicle. This allows for a low, flat floor in the trunk compartment, maximizing luggage space for airport runs, which is the primary bread and butter use case for a ride-hailing vehicle. It also simplifies the rear suspension architecture, likely allowing Tesla to use a cheaper, lighter weight beam or simplified trailing arm setup rather than a premium multi-link configuration. But let's look closer at the 219 horsepower rating. On paper, it sounds low for a Tesla. We are used to sub 4 seconds, 0 to 60 times, and face-melting accelerations thanks to the Plaid. A 219 horsepower motor pulling 3,113 pounds is going to deliver performance that feels remarkably similar to a Toyota Corolla. And that is entirely intentional. This vehicle is not designed to impress driving enthusiasts. It's designed to operate inside an efficiency sweet spot. Electric motors are highly efficient, but they aren't equally efficient across the entire operating range. They have what is called an efficiency map. A massive 300 or 400 horsepower motor operating at very low loads, like crawling through urban traffic at 25 miles per hour, is actually operating outside its peak efficiency island. By sizing the motor down to 163 kilowatts, Tesla ensures that when the Cybercab is navigating dense city centers, the motor is loaded heavily enough to sit right in the center of the most efficient operating zone. Tesla's powertrain team has historically overspec'd motors to get high performance figures. But here, the mandate was completely reversed. Build the smallest, lightest, most thermally stable drive unit possible that can survive 100,000 miles of city stop and go driving without breaking a sweat. Pretty cool idea. Kudos to them. Now let's talk about range, because the raw numbers in the EPA document can be incredibly misleading if you don't know how to read regulatory test cycles. The filing lists the unadjusted combined range at a staggering 418.2 miles, with the unadjusted highway range sitting at 375.4 miles. When mainstream media outlets see those numbers, they immediately print headlines saying Tesla Cybercab achieves 400 miles of range. But let's look at how the regulatory sausage is made. Those 418 and 375-mile figures are the raw, unadjusted results from the EPA's multi-cycle tests. They are generated in a highly controlled laboratory environment on a chassis, dynamometer, zero wind resistance, no climate control running, and a highly stylized driving profile. To convert these raw numbers into actual window sticker fuel economy ratings that consumers see, the EPA applies a standard correction factor, typically multiplying the raw data by roughly, I think it's 0.7, to account for real-world variables like highway wind drag, aggressive acceleration, and running the AC. If you apply the standard 0.7 correction factor to the Cybercab's unadjusted 418.2 mile combined score, you get an adjusted real EPA rating of exactly 292.7 miles, which kind of makes sense for these cars. That lines up perfectly with Tesla's internal projections of close to 300 miles of range. But think about the engineering wizardry required to extract nearly 300 miles of real-world range out of a tiny 48 kilowatt hour battery pack. If you divide 48 kilowatt hours by 293 miles, you get an energy consumption rate of roughly 163 watt hours per mile. That is an industry-leading metric. To put that in perspective, a standard Tesla Model 3 uses around 240 to 250 watt hours per mile. The Cybercab is cutting energy consumption by more than 30% compared to the most efficient sedan on the market today. So, how are they doing it? First, the frontal area of the vehicle is significantly smaller than the Model 3, dramatically lowering the total aerodynamic drag coefficient, even though the vehicle carries some weight. Second, the front wheel drive layout allows for highly aggressive regenerative braking calibration directly on the axle that carries the majority of the vehicle's weight distribution under deceleration. But there is a hidden electrical penalty detailed in the filing that we have to address: the recharge energy. The EPA lists the total recharge energy required to fully replenish the battery from 0 to 100% at 53.365 kilowatt hours. Interesting. Remember, the usable capacity of the battery itself is only about 47.6 kilowatt hours. That means there is a gap of nearly 5.7 kilowatt hours of energy that is drawn from the wall or the charger, but never actually makes into the battery cells. That represents a charging loss of roughly 12%, which is pretty big. For a vehicle that charges via traditional copper cable, a 12% loss would be considered high. Most modern onboard AC chargers operate at around 92 to 95% efficiency, meaning losses are closer to around, I believe, 5 to 8%. But remember, the Cybercab doesn't have a charging port. A lot of people don't remember that. It relies exclusively on wireless inductive charging pads. Inductive charging works by creating an electromagnetic field between the pad on the ground and the receiver mounted underneath the car. While incredibly convenient for an autonomous fleet because no human or robotic arm has to plug something into it, it is physics limited. The air gap between the ground pad and the car kind of creates a flux leakage that generates heat. That 12% total charging loss confirmed by the EPA proves that while Tesla has made massive strides in wireless charging efficiency, fleet operators are still going to pay an energy premium just for the luxury of wireless operation. If you run a fleet, say, of 10,000 Cybercabs driving 200 miles a day, at 12% overhead loss on your charging infrastructure adds up to millions of dollars a year in wasted electricity. It's a classic engineering trade-off, convenience and automation versus pure grid thermodynamic efficiency. Love this stuff. It's the science teacher in me just loves this stuff. The final fascinating piece of data buried in the EPA documents is the official introduction to commerce date, which explicitly listed as May 29, 2026. Because that date is already behind us in our rearview mirror, it confirms that Tesla has legally and technically crossed the regulatory threshold to begin low volume production in internal validation blocks. It matches what we've seen tracking through the manufacturing lines at Giga, Texas, where pre-production units began trickling off the line earlier this spring. But let's close on the macro reality of this entire fouling. And it was very technical, and we gave you a lot of information. From a pure technical spec standpoint, Tesla's engineering teams have delivered exactly what was asked of them. They optimized the powertrain for maximum urban efficiency. They pulled 219 horsepower out of a highly compact front-wheel drive module, and they managed to coax nearly 300 real-world miles out of a sub-50 kilowatt-hour battery pack. That's still mind-boggling to me, setting a new high-water mark for watt-hours per mile efficiency. But as an automotive economist, or just someone who just loves EVs, I look at these specs and realize one critical thing. The hardware is ready, but maybe the business model isn't yet. You can build the most efficient, beautifully packaged, crash-optimized two-seat electric vehicle in human history. You can get it fully certified by the EPA. You can stamp it with an official introduction date, which is what they did. But until Tesla solves unsupervised full self-driving and secures regulatory approval for driverless commercial operation on public roads everywhere, not just a few cities that is geofenced, the Cybercab remains an incredibly advanced, highly efficient answer to a question we aren't legally allowed to answer yet. Without autonomy, a 3,113-pound two-seat front-wheel drive car with no steering wheel and a 12% charging loss, I think it's completely unviable. With autonomy, it's a money-printing machine for urban mobility. The engineering team has done their job. The ball is now entirely in the software and the regulatory court. All right, that's your mini charge episode for today. Before you leave, don't forget to hit that subscribe button and tap that notification icon so you are alerted when new content drops. Also, give our video a hype. If it really does help us on YouTube. We love seeing those videos get hyped. Also, if you're listening on Spotify, Apple Podcasts, or wherever you get your audio podcasts, hit that follow button and leave us a comment. It really helps the show grow. Thanks for watching, and until next time, stay charged and stay geeky. So long, everyone.